going to start talking about waves. Well, a wave is it's a vibration, but we'll be talking about what we call traveling waves first. There are traveling waves and there are standing waves. Standing waves involve a reflection, but we get into that later. So a traveling wave is a vibration moving through a medium with some velocity as it moves through. Now the medium is the material that's undergoing the vibrations. It can be a physical material, like so for ocean waves, the medium is the water. For sound waves, generally we think of the medium being air, although it can be liquid, it can be solid, it's a mechanical vibration. A seismic wave is, the medium is the earth, it's a vibration going through the rock. A light wave, now see, on the analogy of these others, up until the late 19th century, it was thought that light was a vibration of some very thin medium that we could move through without feeling any resistance to it, called the ether. And because every wave that we knew about, we figured that light was a wave. Every wave we knew about had to have a material to physically vibrate. The thing is that it was proven, 1885, I think roughly, Michelson and Morley experiment was a pretty good proof of that the ether did not exist. And while it didn't end that idea all at once, the idea of an ether stayed around for a pretty good while as more experiments added up, people started realizing that the light waves are vibrations of the electromagnetic field, which is a lot more abstract. It's not a material, it's something else. But we can put that off for a few sections. Okay, things about the medium. The medium has to be elastic, meaning that it has to be able to be displaced in one way. Let's say if I've got, looking around for things to stretch. I'm missing it. If it is displaced in one place, so here's the medium. If it's displaced, there is then a restoring force that tries to spring it back to its relaxed position. So in a spring, for example, you've got the restoring force of the spring itself that wants to bring material back to the center point. And that allows for the vibration to propagate. If you take a string, you snap it like that, the string has this wave that moves on through it. Okay, out of these traveling waves, we have two kinds. A transverse wave is a wave where the displacement is perpendicular to the direction of motion. So if you have a string here, and every part of that wave shape is moving with a velocity v along the string itself, by the way, stays hitched. The string is not moving to the right, just the pattern is. But the displacement is up and down, perpendicular to the direction of motion. You also have longitudinal waves. Where the displacement is parallel to the direction of motion. If I draw air molecules, bad here, now, if you have areas of compression where the density is higher and rarefaction where the density is lower, and the wave is moving with velocity v to the right through the air, the individual air molecules are moving forward and backward while the wave is moving along forward. The air molecules are not moving up and down as the wave crosses, they're moving in the direction of the wave and back, and in and back, and so on like this. So, examples of transverse waves, ocean waves. The surface of the ocean is moving up and down. You have a vibration of string, it's another transverse wave. Light waves are transverse waves. Longitudinal waves, examples are sound waves, are probably the best example right there. Okay. The wave speed. So the wave vibration is started, it's initiated by some source that's vibrating. So you've got a source. The vibration travels through the medium with a velocity v. That's the wave speed. I say velocity. Velocity, of course, involves the direction. But a wave speed v. But, as I said, the medium as a whole does not move. As a whole. As the water, if you have a water wave coming past here, the molecules on the surface of the water, as the wave passes, they go up, they come down, so they're moving. But they average around the same position they started off at. When the wave is passed, the water molecule is back to where it was to begin with. It's not that there is a current of water carrying the wave along. It's that there's a vibration around that average position. Okay. So, let me go on with one-dimensional waves, where we can build up our model of how waves work. Before we go on to more complicated two-dimensional cases, or three-dimensional. Now, this is kind of a short section on one-dimensional waves. First, I just want to talk about the graphical ways that we represent the waves. No matter what kind of a wave it is, whether it's a physical surface moving up and down, like in a transverse wave, or if it's a compression and rarefaction, like in a longitudinal wave, we can draw a graph of them the same way. There are two kinds of graphs we're going to deal with. One deals with the wave's shape as a function of position at one moment in time. The second will be the motion of a particular particle of the medium as the wave goes through at one position over time. Let me see. The first one is position at a single moment, so a function of position at one moment. The second is at one position as a function of time. So we have our snapshot graph. This is how the book calls it. Versus our history graph. So, for the snapshot graph, it's a moment in time. So time is fixed, and you're looking at the wave as a function, FCT for function, of, I'll say x, but I mean position. For the history graph, the position is fixed. It's one spot in the medium, even though that will vibrate, of course. And you're looking at its motion as a function of time. So, for example, if we have a simple case of just a pulse, kind of a string, let's say, being snapped out and moving back. So we've got this sort of a hump that moves along the string. Let's take a snapshot graph. At one moment in time, we'll graph the displacement of the string away from its straight position. And we'll use capital D. Let's say that the string was plucked in a certain way. This is a very unlikely kind of a case, but it gives us a shape, where is going to be moving off to the right like this. And on the leading edge, it rises up sharply, and on the trailing edge, it goes descends loosely. Its velocity is to the right. Now, that's at one moment. At the next moment in time, or a short time later, I should say, it has moved a bit more to the right, perhaps given the same shape, exactly. Okay. So this shows the entire string at one moment and then at the next moment. Now the history graph shows a single particle in the string, not the whole length of the string. So we're looking at the displacement again as a function of time. Now, capital D for displacement. In this case, beginning, early times, and going on to later times. So as the sharp leading edge hits the string, we're going forward in time like this. You see that this looks backwards from how that one is drawn. A sharp sweep up and a long decline down like that. It's the same as if we look at a little spot on the screen here. When at the first moment, it rises up steeply, and then as that moment passes, it has a slow decline as the wave passes there. So here's this little spot on it at two different times, early and late. So it's kind of flip the appearance around. This is just to show you what the differences are between those. Okay. Now a note, for a transverse wave, where the medium is vibrating up and down as the wave goes to the right, whichever way it's going. The snapshot graph gives you the appearance, the physical appearance of the actual string, or the water surface, or whatever it is. Because the axes here, displacement versus position horizontally, corresponds to, well, the displacement is perpendicular of the water as it goes past like this. So this is a y versus x plot in this case, and you see up versus to the right when you look at it. But the history graph doesn't necessarily look like that. Now, for longitudinal waves, let me just talk about the snapshot graph. For a longitudinal wave, it won't look like this when you look at it, because you don't really see the wave that clearly. What's happening is that, like for a sound wave, there's a compression going through. And that means that there's a region of greater density where the displacements, well, put it this way, the displacement goes in maybe in this direction, then in that direction, or this way, then that way, whatever it is. And you're not going to see that, but we can graph them the same way. All right. That's what I'll say about that. Okay, displacement, though. We're going to use displacement a lot here. For a one-dimensional wave, like in a string, the displacement is a function of one position coordinate, like x, we'll choose, and time. The displacement is different in different places, and it is different for a given place at different times. So we've got to have it's a function of both variables there. Okay, and the same displacement function can equally well represent a longitudinal wave or a transverse wave. Now, let's go on to the next chalkboard. Sinusoidal waves. A source, the wave source, the thing that vibrates and starts the wave moving. A wave source that oscillates with a simple harmonic motion generates a sinusoidal wave. Now, sinusoidal means you can describe the wave by a cosine or a sine. I mean, sinusoidal means sine, but remember, the shape of a sine function and a cosine function are the same, but they are just shifted one from the other. So the phrase is sinusoidal even if you use a cosine. Now, the frequency of the wave, the frequency f, is the same as the frequency of the oscillating source. So we tie together the wave frequency with the vibrating source frequency. They're going to be the same. So let me give if we've got a sine wave, we've got a snapshot graph or a history graph. Displacement is on the vertical axis. Displacement is a distance. How far a particle in the medium has moved away from its relaxed position. So let's say it's put in meters. At one snapshot in time, I'm looking at the displacement at different places. So let's say we've got a perfect sine wave here, a sinusoidal wave. There. Things to measure about this. The distance, obviously we've got a crest here and a trough here. The lowest points are the troughs, the tops are the crests. Now, the distance from one crest to the next is the wavelength. We use the Greek letter lowercase lambda. Okay, that's lambda, which is the Greek letter L. It is a length, it is given in meters, or whichever units are appropriate, but distance units. Now remember, we tend to use Greek letters when we're dealing with oscillations and rotational motion. Lambda is L, and L stands for length, so it's just length here. All right, and that's the distance between any two successive crests. It's also the distance between any two successive troughs, but we'll tend to measure them from crest to crest. Okay, and let's say the wave is moving here with speed, wave speed v. A history graph. Okay. Oh, I'm sorry. We're not plotting versus position. We're plotting versus time now. Now, I'm not going to draw it precisely. I'm not going to draw it crossing the origin at position at crossing the origin necessarily, because I don't want you to be confused between plotting versus x and plotting versus t. They don't have to look precisely the same, lined up with each other. They're just going to have the same basic sine shape. So let me have this drawn like that. A little different. But it's still a sine wave. I've still got the same amplitude. Still got displacement there in meters. Now in this case, the distance in time from one crest to the next is not the wavelength. That's a length, that's the distance. It's a time I'm measuring here. The time it takes to go from one crest to the next is the period, capital T. Measured in seconds, for example. Okay, so that means that the period on a history graph corresponds to the wavelength on a snapshot graph. So period meaning the time between successive crests, is the time that corresponds to the distance shown by the wavelength. All right, let's tie these in together. The fundamental relationship for sinusoidal waves is that the velocity of a wave, now, velocity of anything is the distance traveled in a certain amount of time. DIST for distance. That's my definition of what velocity is, distance over time. So, the velocity, a wave traveling with velocity v travels, say, the point on the crest. That crest, not the particle that's up there because it stays put. The crest itself, the shape, moves a distance lambda in a time t, a period, capital T. Now, because you can recall that frequency is 1 over the period, we can put that in there. And we come up with a really useful equation. Velocity is equal to the wavelength times the frequency. And we're going to use this over and over and over again. Okay. Next I want to get on to the mathematics of these sinusoidal waves. This is going to take, there's a lot more detail in here. I'll start back on the first chalkboard. Okay. To give you a sense of why we're going to have these, or of some of the terms we're going to be using, recall from the chapter on simple harmonic oscillators that the position of a sinusoidal, a simple harmonic oscillator, a source of a wave that's undergoing simple harmonic motion, its position will be given by, so for simple harmonic oscillation, position with respect to time is given by an amplitude times the cosine, or just as well as sine, of omega t plus phi naught, our initial phase. So, since omega is 2 pi times the frequency, and the frequency, let's see, the frequency is 1 over t, we can substitute that in here to get also a cosine 2 pi times time, lowercase t, over period, capital T, plus phi naught. Okay. Now, that's just for analogy for what we're about to do. We've got a source moving like that, although we could put it in terms of the sine. It would just change the phase by 90 degrees for 2 pi radians. Sorry, pi over 2 radians. Okay. So let me start off our wave description. Let's see. If we look at a sinusoidal wave at the initial time, t equals 0, then the displacement function, capital D, which is a function of position x and time t, so I'm setting time equal to 0 in here. Displacement of, as a function of x and set time equals 0, is equal to a times, we've been using the sine for the waves here, times sine of 2 pi times x over lambda plus phi naught, the phase constant, the initial phase. Now notice, I've been saying the phase constant, the initial phase. All of this together, inside the parentheses of the sine, we call this the argument of the sine function. This is the phase. Not the initial phase, that's only at time 0, but the phase, phi. And the phase, of course, is a function of time, as I went on about with the connecting it to circular motion. So, when I refer to the phase, it's the whole thing inside the sine function. Now, notice here, just like I did a moment ago with the oscillating source, it varied to cosine or whatever of 2 pi t over capital T plus phi naught. Here we have the spatial equivalent of that there, where we're looking at x position as a fraction of a full wavelength. Just like before, I was showing it for the simple harmonic oscillator, the time as a fraction of the full period. Those go together. So by putting it here, x over lambda, x is in meters, lambda is in meters, the dimensions cancel out. I'm left with a dimensionless number. Phase constant is also dimensionless. It's in radians, which are dimensionless. And the whole thing, the phase, has to be a dimensionless number, varying from 0 to 2 pi radians, and then repeating as you go and farther beyond that. Okay. So, the displacement, graphed as a function of x. Remember that the distance between those is lambda, the wavelength. And so I'm looking at where I am within that there. Now, notice that a sine and a cosine function are exactly periodic. I get the same value for the whole sine function at this point, at this crest, as I do at that crest, and as I would at the next crest. It's got the same height then. Or if I'm here, you know, maybe it's 1/4, let's see, maybe it's 1/8 of the way into that wave past the crest. I get the same height at any point that far in. Okay. So, a wave moving in the positive x direction with a velocity v. That was at the initial time. Now let's generalize it to time t. The displacement as a function of x and t is going to be equal to the amplitude a times the sine of 2 pi times x minus vt all over lambda plus phi naught. Now you look at this and think, my goodness, where did the minus dt come from? Well, that's actually one of the annoying things. But recall, let's see here. Think of this. Given, if I just gave you this, you could recover what we already had, and we agreed looked pretty fine. Just diagonally this. If t equals 0, then you got x over lambda, just like this. Our displacement is a function at t equals 0. As t increases, now you're not going backwards in time, but as t increases then, this gets you at a given velocity. It gets you the motion of the wave going in the positive direction. Let me just build on that there. Doesn't look immediately obvious, but recall that wave speed is wavelength times frequency, lambda f, and f is 1 over the period. So if I put in, I've got v is lambda over capital T. I put that in. Now I'm going to rearrange it a little. Let's see. I need to use square brackets here. If I put those in here, and I split that fraction up into 2, then I've got x over lambda minus, you get a lambda over lambda, which cancel out, lowercase t over capital T, and then plus the phase constant. Now, do the algebra yourself. I don't have the room on this very small chalkboard to fit it in. But that will come out this way. Now look here. Now I've got a ratio of position as a fraction of wavelength minus time as a fraction of period. Nice parallelism going on there. Okay. Now this is exactly what was written here, but in terms of wavelength and period both. Okay. Now what do I want to do? I'd like to put it in terms of the angular frequency, the angular components here. Let me erase this for space reasons. Okay. Using this, recalling that angular frequency is 2 pi times f, and therefore it's 2 pi over the period t. Let's define a spatial term that corresponds to this time-based term here. So angular frequency omega corresponds to 2 pi radians divided by the period. So let's define something called the wave number. We're going to use a lowercase k. I tend to write my lowercase k's somewhat script in form to tell them apart from the capitals. Defined as 2 pi over lambda. Unfortunately, since I'm using lowercase k, this looks an awful lot like the spring constant that we discussed when going over the simple harmonic motion. It's not. It's not even related to it. It just happens to have the same letter. And it appears in different places. But because the simple harmonic motion, which often involves a spring, can give rise to a sinusoidal wave that can be defined by a wave number, unfortunately, you may see them coming up in the same kinds of problems, at which point someone might, a book might throw in one of them as being a capital, just to clarify. Now, the wave number, this has dimensions of radians over meters, length anyway. Which, because the radian is really a dimensionless unit, can also just be written as 1 over length, 1 over meters. Just like that has dimensions of radians over seconds, or just 1 over seconds, or hertz. Okay, now, the wave number depends only on the wavelength. Basically, inverse wavelength, there's that 2 pi factor. So if you know the wave number, if you specify the wave number, you've already specified the wavelength. Given one, you've got the other. So, but if we've got the angular terms here, it's easier to talk about wave number rather than wavelength. All right. So, given these, recall that wave speed is wavelength times frequency. Let's put in frequency is omega over 2 pi. Wavelength is going to be 2 pi over k, wave number. You put those together, the 2 pi's cancel out. The wave speed is omega over k, angular frequency over wave number, or you could write it as omega equals Vk. Yes. Either one of these is a useful form to have. So we can relate the angular frequency and the wave number to the wave speed. All right. Let's see here. Now, given this one right here, I've got the displacement function as a function of position x and time t. I can, and wavelength and period. I can put it in terms of omega and k there. So given this over here, I think I'm going to have to move the camera again. Okay, so A sine times 2 pi. Now, here we get a little tricky. I had x over lambda. So that is, if lambda is 2 pi over k, minus, I have t over capital T. Let's see here. So that's going to mean 2 pi over capital T is omega. So T is 2 pi over omega. Close parentheses, plus the phase constant, phi bar. Okay, now, let's put these in the numerator. So I've got 2 pi times parentheses kx over 2 pi minus omega t over 2 pi, close parentheses, plus the phase constant. I multiply through by 2 pi, that cancels out the denominator 2 pi's. And I can go back to using the parentheses now, because I've only got just a sum of 3 terms in there. And now I've written the wave function, the displacement function for the wave is the wave function, in terms of these angular quantities, wave number, angular velocity. This is a convenient form to put it in as well. This gives you exactly the same information that was over here before, but in slightly different variables, different parameters that you might find useful. Now, all of this, I should say, all of this was for a wave moving to the right in the positive x direction. And that meant that we had to have this minus sign here, and for that matter, here. Moving in the positive x VAR for direction. If it was going in the negative x direction, you would have a positive sign here. That seems a little contradictory, but remember, this is for increasing time, not increasing position. Goes in the other way. All right. One other thing, so I mentioned it before. That all of this mess inside the parentheses, inside the sine function, is the wave phase. So the wave phase, phi, is kx plus or minus. I should say, let me put minus or plus, because going to the right is with the minus sign. Minus or plus omega t plus phi naught. And you know, we normally plot a sine function as a function of phi, or theta, or whatever angle. So that's what that is right there. It's a dimensionless number, because you can't take the sign of something that has units on it. Dimensionless, well, aside from degrees, but you know, that's angles are dimensionless. A dimensionless number corresponding to the phase, the angle in circular motion. Okay. Let's find out, for a specific case, for a wave in a vibrating string, how fast does the wave move through the medium? Now, the book has, this is a really convoluted section of the book, about 2 pages where it just seems to go over and back and forth and it doesn't make much sense to me. So I've reorganized this. What we want to find is, for a one-dimensional wave, which is all we've dealt with so far, in a vibrating string that has a certain tension applied to it, how fast does the wave move? So, let's start off with, okay, let me see here. Let's start off with Newton's second law. F equals ma. Sum of the forces, F equals ma. The second law is a very convenient starting point for most classical mechanics problems. Now, let's look just at the vertical motion, the displacement of the material in the medium. So y versus x, where the displacement is in the y direction. Okay, so if we take the y component, sum of forces in the y direction equals m a sub y. Now, the reason I'm doing this is I need to get to velocity, not the velocity in the vertical direction, or that's what immediately I'm going to come across, but the velocity in the x direction. Not for the material, which doesn't move left or right at all, but for the wave pattern. Turns out I'll be able to tie that in. It's not immediately obvious. In fact, it's not even really obvious when we get to it, but you can, when we get to it, I think you'll see what we're doing. All right, so first, let's take the acceleration that's vertical. That's the second derivative with respect to position of y. It's the second derivative of y with respect to t, time, not the other way. Now, the reason for looking in the vertical is that the displacement function is the vertical position here, y. So y, I just write in the wave function here. Let's see, y of x and t is a times the sine of, parentheses, kx minus omega t plus phi naught, the phase constant. Now, you take the first derivative, you get out, let's see, you're taking it with respect to time, t. So you get out a factor of minus omega. The first derivative of kx is 0. First derivative of phi naught with respect to t is 0. Those are all constant with respect to time. You get out minus omega out front. Take the derivative of the sine, you get the cosine. So you get a minus omega, a cosine, and blah, the same stuff. You take the second derivative, so you take the derivative again. Now you get another factor of minus omega, pull it out front, and you get from the derivative of the cosine gives you the minus sine. So the second derivative then, plug that in there. So your second derivative is, oh, you know what, I'm just going to write it in here. I don't have a lot of space. So I've got an m, I've got minus m omega squared a sine of kx minus omega t plus phi. Right. Mass times acceleration. All right. Now here's the thing though. The mass of the whole string, well, no, that'd be a little bit tricky to do, right? Because what if you have an infinitely long string? What we are really looking at is the motion of a little tiny piece of the string at one time. And we're going to be able to deal with the force on that little tiny piece of the string, rather than trying to deal with the forces through the entire one. So we'll look at a little segment right up there at the crest of the wave. Now, if we've got this continuous material like this, what I'm interested in is the mass per unit length. That's the linear mass density. So if you have normal density is mass per volume, because we have 3 dimensions in space. But you can talk about the surface density, the 2-dimensional density of a more or less 2-dimensional material, like a piece of paper. I mean, yeah, it has thickness and so on, but per surface area. Or for a string, you can talk about the linear 1-dimensional density, which is mass per unit length. And for that, we use the Greek letter mu. Let's see here. So, So we'll use, instead of m, we'll solve for m in terms of the density. So if we define mu, which looks like an m, but it's with a long descender in the front, and it's pointed, mu is defined as mass per length. Now, we're going to deal with a little tiny piece up here. So let's deal with the mass over a region delta x, which is the width of that little section. Therefore, solving for m, we get mu delta x. Now, that sets us up nicely to solve for the forces on that little tiny piece there. So, if I look at, let's let the wave get to the point where the crest, one of the crests, is centered around the origin. Whatever time that happens to be, it doesn't matter. All right, so there's the wave crest, roughly, my drawing centered on the origin. Now, my segment of string, there we go, has a width delta x, okay? And so the tip ends, there's the origin there. This end is at a position minus delta x over 2, and this end is at a position positive delta x over 2. What about the forces acting on this? Okay, if we're looking at the forces where those tip ends are, the rest of the string is exerting a tension force. I'm going to erase the curve here. Tension in the string, or tension along the, no, I don't think, the book uses a subscript s. I don't think we even need that. There's the tension force there. There's the tension force there. Again, evaluated at the tip ends. And the tension force is an angle theta down from the horizontal, the crest is. Okay. Yeah. Now, draw a force diagram for that string and those two forces on it. So we've got y and x. So if I just draw the string as a dot there, I have tension force here, tension force there. I'm looking at the y component, so I need to solve for that. Let me draw the T on that side and the T there. I've got right triangles. So this is T sub y. That is T sub y. I've got an angle theta and theta. Now that means taking my harmonic, the SOHCAHTOA harmonic. Let's just take this right-hand one here. This is the side opposite the angle. This is the hypotenuse. And this here is the side adjacent to the angle. So, opposite hypotenuse, I've got those two. This is what I want, that's what I've got. So the sine of theta is equal to T sub y over T. Therefore, T sine theta equals t sub y. And remember, I needed the y component of the force. Okay, now substituting in, yeah, that gets me to where I want to be. So let's take this here, and let's sub in mass is the density times that little, the mass of the little section is its linear density times its length, and that's put in for the forces. We've got t sub y plus t sub y. Facing down there. Rewriting my force equation. So, sum of the forces, 2 times t sub y. Actually, I forgot to write down the reason why that we have a positive sign here. The book does explain it. See that. I forgot what it is right now. So now I've got mu is m over delta x, so m is mu delta x. So I've got minus mu delta x times omega squared a times, now let's see, we've got the wave is centered on 0. So the position here, we know that the phase is going to be such that the value of the sine has to be 1. That's its maximum value for the sine. And we're at the crest, so we're at the maximum value, so times 1. Okay. And we didn't even specify what the time was. We just said at a time such that where the crest is at the top. The crest is centered here. All right, now, let's see. We put in t sine theta. Equals negative mu delta x omega squared a. Now, let's recall that here's where we finally get the wave speed, which is what we're solving for. Omega is v times the wave number k. We found that a few minutes ago. We put that in, and so we've got v squared k squared where omega squared was. Okay, now for the sine, we're going to use the small angle approximation here. Like we're going to use it twice in different ways. The first is that we were able to get, we found that ty was equal to t sine theta. That's absolutely true. But it turns out that life would be a little easier if we looked at the tangent of theta. The reason is that the tangent will be equal to the slope of the wave as it comes down. And that will be, we can take the derivative, the slope is the derivative of the graph. And so we're going to get a derivative, and derivatives tend to simplify things. All right. So for the small angle approximation, if we take a short enough segment, then the edges are pointing down only at a very shallow angle. So the angle is going to be small. Small angle approximation. Given that, so for a small angle, the sine is about equal to, well, we've got our choices. In this case, we're going to say it's about equal to the tangent of theta. And then we use the fact that the tangent of a curve, of a graph, is equal to its slope at that point. Or the tangent of that, using the word tangent in a different meaning, sorry. The tangent of this here is the slope. Tangent of theta is the slope of that point. Okay. dy by dx. Okay, well, what is the derivative? I'm going to erase this here for now. Making sure that this is still visible. Yeah. The derivative, dy by dx, evaluated at the point, let's take the little right-hand spot where it's going down, x equals delta x over 2. So the right-hand edge of our little segment of string. So that's the derivative with respect to x of the wave function. Now, we've got this long, complicated sine function. But we can also use the fact that when the wave is centered, where a crest is centered at the origin, all of the stuff in the phase works out such that the whole wave shape is equal to the cosine. Cosines always have their crest centered at the origin, a crest centered there. So I'm using another trick. That means that at this point, omega t plus phi naught has to equal 0. That will make it come out to be the cosine there. So we just did this based on the shape that we looked at. It's obviously a cosine in terms of x. Say obviously after I point it out. All right, we take the derivative with respect to x, and we'll evaluate it at delta x over 2. This is equal to negative ka times sine of kx, where, that's the evaluation bar, x equals delta x over 2. So I have to substitute that in for x. K delta x over 2. Now we'll use one other trick. Remember that I said that we got a very short segment of string we're looking at. That means delta x is tiny, right? If delta x is tiny, sine of all of this, well, all of this here is very small. Therefore, we can use the small angle approximation again. For a very tiny length of string, we've got a small angle approximation. So sine of k delta x over 2 is about equal to k delta x over 2. So it may be too small for you to see, but listen to what I'm saying. That means we've got negative ka parentheses times k delta x over 2, and we're left with negative 1/2 k squared a times delta x. That's the derivative at that point. And you feel, wow, that's so enlightening here. I had no idea it was like this. All right, so what do we do with this? So we take this, and we're going to substitute it in here. 2 and the 1/2 cancel out. So we've got here, let's see, minus, I'll bring the minus sign out front, 2t times 1/2 k squared a delta x equals negative mu delta x v squared, that's a k squared a. Now we get to cancel. The negative signs cancel out. 1/2 and 2 cancel. K squared and k squared, a and a. And we are left with, be very careful about how you drew this, t delta x equals, oh, and the delta x is canceled. T equals positive mu v squared. All right? Solve for the velocity now. Now it just simplified right away. It wasn't obvious that that was going to happen at all. And I just about guarantee you the first guy to figure this out did not say, do this in the space of, what is it now, 15, 20 minutes, and out it popped. He probably hunted and pegged around and pulled his hair out a number of times. But finally, hit on it. Solve for V. You can see that V equals the square root of the tension divided by the linear density. T, by the way, is not the period. You know what? That's probably why the book used T sub s in the first place. Well, be that as it Okay. That means if you tighten the string, you get a greater tension. The wave travels faster. And you instinctively notice if you've ever played around with your brother or sister holding a rope, and you pull the rope out and you snap it like this, and you get, or a hose, a garden hose, the wave will move on through it. If you tighten it, you can see the thing speed up. Also, it travels faster in a lighter weight material. So if mu is smaller, the density per, mass per unit length is smaller, but weighs less, you get a faster wave. You get a very light, thin string. You get a faster wave, but if you get a heavy cable or something like that, it's a very sluggish kind of wave. Okay, let's continue on with something that's really a bit more qualitative. Two-dimensional and three-dimensional waves. Things going to sleep. Okay. So far we've been dealing only with one-dimensional waves because we only had a single position coordinate, x, to deal with. Made it simpler. Now we can start to generalize this a bit. If we're dealing with, well, let's see here, in one dimension, 2D and 3D waves. Now, what kinds of waves have these different dimensions? A one-dimensional wave, a good example is vibrating string. For a 2D wave, an ocean wave that travels on the surface. For a 3D wave, sound waves that travel through all 3 dimensions of space. So what we're going to do, whereas before, with a 1-dimensional wave, we could draw the whole wave shape there. It's inconvenient to do, even for a 2-dimensional wave. Let's say if we had the surface of the chalkboard were the ocean surface, we can't draw up and down like this. We could try drawing chalk marks to represent the height on there, and in practice what we wind up doing is just we draw the wave crest positions, spread out in lines. So what we call a wave front. A line of crests. Whether it's in 2 dimensions or 3 dimensions. Of course, for 3 dimensions, we've got to take a slice through it, a 2-dimensional slice through it in practice. Okay, now, for example, if we have if our vibrating source that generates the wave, if it is very small compared to the wave length, essentially it's a point, a dot. All right? In that case then, the wave, as it spreads out, and that's the thing about waves, they spread. And they spread naturally in a spherical, for 3 dimensions, or circular, for 2 dimensions, shape, directions around the source. If the source is small compared to the wavelength, then they spread out in effectively a perfect circle or a perfect sphere. We'll call them circular waves for 2 dimensions or spherical waves for 3 dimensions. So, if I've got my source there, little vibrating source, and I just draw where the wave crests are around it, it's starting to get lopsided, but it shouldn't be. Okay, if you'll assume that those are all perfectly concentric, perfect circles, then there's my source. If I draw the up and down motion of the section of the wave moving out to the right, then you can see that you'd have here crest, crest, crest. Oh boy, I'm lumping up a bit too much. Crest, crest. Like I said, they got too compressed here, and they shouldn't. So this wave front, think of like a weather front, is the line of places that all have the crest at that place at that time. There are the crests. Now, all of these are moving out away from the source with a speed v. And so on. Each one of these wave fronts moving outward at speed v. Now, these are spaced out. Well, the distance between 2 crests is called the wavelength. So all of these wave fronts are separated by a distance lambda, the wavelength. Notice something though, even accounting for my bad drawing here. As you get farther away from the source, the wave front gets straighter and straighter. This means, really this is just that a circle or a sphere of a larger radius is flat on any little segment of it. So the wave fronts are very circular or very spherical, close to the source. But as you get farther away, as your distance approaches infinity, the wave fronts approach the shape, meaning they, in this limit, they become approximately parallel lines. For 2 dimensions or parallel planes for 3 dimensions. So very far from the source, as x approaches infinity, or as the radius, distance, r approaches infinity. And these are what we call plane waves. So here, this would mean that all of the crests they're all moving. Every individual little section of a wave is moving parallel to the others in the same direction. Here, close in, they are visibly spreading out away from each other. But when you get very, very far away over any small enough section, they are plane wave. They become plane waves where each section of a wave is moving together in the same direction with the same speed. This, looking far away from the source then, simplifies life. Because even though, yes, there's still a very slight divergence, you never get truly plane waves in nature. But you can get so close to it that it just doesn't matter. And whereas we get complications dealing with these circular waves, or the spherical waves, because as they spread out, the amplitude decreases. The amplitude becomes a function of the radius of the circle that it's on. And so it gets smaller as it goes out because the same amount of stuff has to be spread out over a larger area. So there's less amplitude to go around at any point. It's a crude way of putting it. Okay. Let's see here. So we will, for circular and spherical waves, the displacement will be written as a function of r and t, where r is the distance from the source. But for plane waves, one-dimensional vibrating stream, we only use the position x. But for plane waves in 2 or 3 dimensions, we can also use the position x. We don't have to worry about the distance from the source because plane waves don't change as they go on. And the amplitude stays constant. Okay. Finally, we'll finish up today with the phase difference. This you probably already know something about, whether you've had the mathematics of it or not. Remember that dealing with, say, just a one-dimensional or a plane wave, so I can use the coordinate x rather than having to deal with r. In its most basic form, our wave function is amplitude times the sine of phi, where phi is the phase. A dimensionless number, effectively it's in radians, going from 0 to 2 pi, or beyond that, or to negative, but it's cycles. So that phase is a function of position of time. If we expand that, putting in the usual way that we have it written, a sine of kx minus omega t plus our initial phase, the phase constant. All of that together is phi. Okay. If we were to graph this out here, if we draw the displacement, that wave shape, as a function of the plain old sine waves, a function of the phase, phi there. Well, if it's a sine, put that in radians here. Pi over 2, pi, 3 pi over 2, 2 pi, and continuing on. I'm going to draw this better. There. eighth sine of phi. There it is. Now, if I want to know about the difference in phase between any 2 points on the wave, say between this point here and that point there, whatever the value of phi is here, say phi 1, and the value of phi here, say phi 2, the difference between those is just delta phi, phi 2 minus phi 1. Remember, we take the final minus the initial, second minus the first. Okay, and we're talking about this phase difference is how far across the cycle have we gone in radians. But we can put that in terms of different positions, in terms of x. If we're graphing this the same wave in terms of x rather than in terms of the phase itself. Okay, so we've got to put in that phase is kx minus omega t plus phi naught. There's our wavelength lambda. Okay? Now, for those 2 points, wherever those happen to be on the phase, they will have 2 different places in position. Okay, so they're separated by a distance in space that is delta x, a difference in position. That's not the phase difference. Delta phi is the phase difference. So let's see what that looks like. And this is what we'll finish up with. I've already written phase difference now. Well, anyway, so delta phi is equal to, by definition, phi 2 minus phi 1. Now, phi is kx minus omega t plus phi. So I put in the first one. kx1 minus omega t plus phi naught. Close parentheses, minus for the second one. kx2 minus omega t plus phi naught. Minus the first one. kx1 minus omega t plus phi naught. Now, we're talking about 2 different places on the same string at the same time. It's on the same wave. So I don't have 2 different times. Not T1, T2, it's just T. The time I'm looking at this. The only difference is in where on the string they are. So when I carry this minus sign all the way through, I've got kx2 minus kx1 plus, minus omega t plus omega t plus phi naught minus phi naught. Cancel, 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 and I'm left with the wave number k times x2 minus x1, which is k times delta x. So, the phase difference, delta phi, is the wave number times the difference in position. Let me erase this and I'll write the last little bit up here. Because since that is, let's see, k delta x. But remember that k is defined as 2 pi radians over the wavelength. Now this is where it gets to be useful. Because the wavelength is length, delta x is length, we get a dimensionless quantity. There. So phase difference is a matter of 2 pi radians times what fraction of the wavelength have we moved along. If these 2 points are separated by a very little distance compared to the long wavelength, they're in almost the same phase. There's very little phase difference. But if they're separated by a large amount, large fraction of the wavelength, they have a very large phase difference. If they are separated by exactly one wavelength, what would the phase difference be? The delta x is lambda.
You threw me off the last thing you said.
Okay.
If delta x is lambda.
If delta x equals lambda, you know, how far apart?
Oh, so just 2 pi.
2 pi. 2 pi radians.
Mm-hmm.
Now, since the sine function is exactly periodic with over 2 pi radians, they would have no phase difference then if they were that far apart. Let's see. Actually, I want to graph that in terms of x. There we go. So if you've got any 2 points on adjacent crests, they have lambda over lambda. They've got 2 pi radian phase difference, which is the same as none, because phase goes from 0 to 2 pi, and then it repeats. 4 pi is the same as 2 pi is the same as 0, and so on. And so when we draw these wave fronts, when we go out, they are at the same phase as each other. When we talk about being 180 degrees out of phase, or pi radians out of phase, it's like from crest to trough, kind of a difference there. All right, here into the lesson.